Good afternoon, everyone. My name is Ashley Kutsia, and I'm the chair of the SANCOLD Young Persons Forum. It is my pleasure to welcome you to today's webinar, and thank you all for taking the time to join us. Today's session focuses on ambient vibration testing of concrete dams, an increasingly important field within structural engineering and dam safety. Before we begin, just a few housekeeping notes. Today's session is being recorded, and the recording will be shared on LinkedIn after the webinar. All microphones and cameras have been disabled to minimize background noise during the presentation, but please feel free to post questions in the chat throughout the session. We will address them during the question and answers at the end. If you prefer to ask your question verbally, you are welcome to raise your hand and I will enable your microphone during the discussion session. It is now my pleasure to introduce today's speakers. We have Professor Pilot Moyo from the University of Cape Town. He is a professor of structural engineering and director of the Concrete Materials and Structural Integrity Research Unit at the university. He previously served as head of Department of Civil Engineering and as Deputy Dean for Research and Postgraduate Studies in the Faculty of Engineering and the Built Environment. He is a registered professional engineer with EXA, a fellow of the South African Academy of Engineering, a fellow of SAICI, and a member of the Academy of Science of South Africa. Professor Moyo's research focuses on structural health monitoring, condition assessment of civil infrastructure, and vibration serviceability, with particular emphasis on railway bridges and concrete dams. He has authored more than 140 peer-reviewed publications, supervised over 70 postgraduate students, and advised governments, utilities, and dam authorities across Africa and internationally on major infrastructure integrity. Joining him today is Dr. Nyoni, a recent PhD graduate and currently a postdoctoral research fellow in the Concrete Materials and Structural Integrity Research Unit at the University of Cape Town. Dr. Nyoni's research has largely focused on the numerical modeling of concrete dams, including ASR modeling and model updating for reliable dam safety evaluation. His current research focuses on infrastructure resilience to climate change-related hazards, with particular emphasis on computational modeling, structural health monitoring, and digital twinning. Prof. Moyo and Dr. Nyoni, thank you for joining us and for sharing your expertise with the SANCOLD community. The floor is yours.
Thanks very much, Ashley. Am I audible?
Yes, you're audible, and we can see the slide too.
Okay, thank you very much. Good afternoon, everyone. Thanks very much for joining us this afternoon in this webinar on ambient vibration testing of dams. As Ashley has introduced me, my name is Pilot Moyo. I'm from the Department of Civil Engineering at the University of Cape Town. And this afternoon, we'll walk you through ambient vibration testing. As Ashley also just indicated, I'm the director of COMSAIRU. But you will also notice that there is another little logo there which says Urban and Public Infrastructure Research Initiative. It's an area that we're increasingly working on, which is largely looking at infrastructure management, infrastructure policy-related issues. So just to kick us off, somehow my slides are not moving. Just give me a minute. Ashley, I might need to reset my slides. They don't seem to be moving forward as expected. Let me re-share. Okay, now we fix that. So just to start us off, this afternoon, I will want to just reflect a bit on dam safety management. And dam safety is, of course, intends to ensure structural integrity. And our intention really is to protect people, property, and the environment. And in South Africa, dam safety management is actually legislated in law that through the National Water Act. But there's another legislation which increasingly becoming important, which is the so-called Giyama Government Immovable Assets Act, which deals with managing of government assets and focuses a lot on asset management principles and life cycle management. But I'll focus more on the technical side this afternoon of dam safety evaluations, which really take these three main activities, which is visual inspection, surveillance and monitoring, and numerical modeling. And through these activities, the intention is to gain as much information in order to make decisions about the condition of the dam or a reservoir, if the reservoir in that case. And once we get that state of health of the dam, then we can obviously make a decision as to what is the next step. The best case scenario would be, after doing your visual inspections and after looking at your monitoring data and your model, to have a perfect match between what you have modeled or assessed and the actual structure. And of course, we know this is not possible. There's always going to be a misalignment, and the essence is to minimize that misalignment as much as possible as one goes through the assessment phase of a dam. And one of the biggest challenges or the complexities with dams is the many issues that interact around these structures. And we know dams are very complex structures. They present challenges throughout the activities of dam safety evaluation, from inspections to numerical modeling. There are significant challenges. Most of these arise from the complex geometry of the structures. They are not, we can design it as symmetrical, but they will never be perfectly symmetrical. The foundations will often offer challenges. The dam wall itself, the environment in which the structure is placed. As engineers, we have to put all of these together to come up with a meaningful solution or a meaningful interpretation of what is going on with the structure. And noting that misalignment will lead to difficult or rather inaccurate decisions. And if I was to inspect a dam, it's going to be unlikely that I will see everything on that dam. Neither can I monitor every piece of that dam. Neither can the numerical model that I create be a perfect match to the dam. So my intention, of course, as a dam safety evaluator would be to minimize that difference between what is in my head from my inspections, or what I see from the data that's coming out of the instruments, or what I see in my model. So try and minimize that and bring it as close as possible to the actual structural system, or to the actual structure as it stands. So I want to focus, we'll focus quite a bit on the numerical modeling, because this is where ambient vibration testing plays a role. And look at the processes, the process of modeling. What are the key limiting factors? So I'm showing this picture. You'll see quite a bit of it today, which is one of the dams in the Western Cape. Given a dam like this, with the intention of assessing and evaluating the condition of this dam numerically, one wants to create a model, whether it's a finite element model or a simple structural model, that mimics this structure as closely as possible. So I want what's out there on the ground to be as close, or to behave as close as possible to what's in my computer. And to do this, one draws a lot from existing information through visual inspections. So you can you spend time investigating or looking at the structure, or from data that you collect from monitoring instrumentation, or geodetic measurements, crack gauges, and so on. So you bring all of this information to inform the model that comes out of your that you build in your computer. So noting that, of course, the more there's a discrepancy between the structure and the computer or the model, the more you are going into or getting inaccurate conclusions, which may have an impact, of course, in the decisions that you make. So our intention really is to bring this to as close as possible, whichever approach we take. At the end, if we can bring this to, from a numerical modeling point of view, if we can bring the actual structure as close as possible to what's in my computer, then I can make significant or appropriate judgment about the structure. So how do we normally do this? We would look at available information, build the models, and we try and calibrate or validate using as much information as possible, largely static type data, geodetic measurements. We could even bring in temperature effects. We could bring in the varying water levels, which may change from time to time. The question is this adequate to capture the complex behavior of dams? And I'll try to just use one observation that we have made from monitoring one of the dams here in the Western Cape, and that is monitoring displacements over time. An interesting observation is on the graphs that you see on the screen there. There is displacement versus ambient temperature. You can see there's quite a good correlation between displacements and temperature. Obviously, the wider band is because of seasonal effects. But interestingly, there is some interesting behavior between the water level and the displacements. We see, in particular, when the dam is full, around 48 plus meters there, you see quite a range of displacements over that capacity, or over that volume of water. One would expect a narrower range. And you also see in the red line there, an increase in the displacement. And what we observe is that that's generally over a short period of time, and it's related to the dam filling up. And once the dam fills up, its displacement continues to change with time. And this is really indicating that the seasonal temperature variations drive the displacement behavior a lot. This is, of course, in areas where there's significant seasonal temperature variations. In areas where there is very little temperature variations over the year, like closer to the equator, this might not necessarily be true. And so we also see that there's rapid filling. During rapid filling, we can obviously see the hydrostatic load, the hydrostatic effect on the displacement of the dam. But what this is also telling us is that if I was to create a model, it becomes a little bit more complex because I have to bring in the temperature effects somehow. I have to also account for the hydrostatic load. And we know we can easily associate the hydrostatic load with the stiffness of the dam, but how do we deal with the temperature effects in a way that captures the displacement behavior of the dam? So this is one of the things that led us to start thinking differently about how to develop models that speak to the structure as it stands. So the idea of vibration or testing is well known and it's been in existence for a long time. And it's been used for linking models to finite elements via certain dynamic properties such as natural frequencies, mode shapes, and damping ratios. Why is this such a useful property? Is that the mass, the damping, and the stiffness are inherent properties of a structure, so they won't change. They as a signature to the structure. So if I can find these properties today, they should be repeatable. I should find the same properties over time unless something has happened to the structure, some damage has been introduced. We also observe for dams that there's a little bit of a complexity. That is, the water level keeps changing, so we have this phenomenon of added mass that we have to account for when we are modeling these structures. So generally, the premise for dynamic testing is that the mass, the stiffness, and the damping are inherent to the structure, but these are also linked to the dynamic properties such as mode shapes and natural frequencies. And how do these mode shapes and natural frequencies look like? This is a typical mode shape for a dam, almost displacement type behavior, but these are linked to vibration modes. So the beauty of this is that you have the theoretical model, which is the meshed dynamic model, and you can measure this on site and reproduce the same properties from the actual structure. In a way, in the similar way, you can also measure the natural frequencies and you can connect them to the stiffness of the structure. And if we can achieve this, then we probably have now an opportunity to access the true behavior of the structure in terms of its stiffness. And one of the good things about looking at this combination of mode shapes and natural frequencies is that the mode shape will give you a good sense of the distribution of the stiffness in the structure. And the natural frequency, of course, gives you the magnitude or the values of the stiffness. We know, of course, that the stiffness, which I have represented there as Kn, is connected to E, or the Young's modulus of the system. And in our case here, the mass Mn keeps changing according to the water level. So we now have this possibility of the theoretical mode shape and measured mode shape, and our intention is to bring this as close as possible by adjusting the Young's modulus, and also adjusting this, obviously adjusting the stiffness of the structure, but in a systematic way that brings the frequency and the mode shape together. If we don't do that, we can adjust the structure to match any condition that we want. But if we pull these together, we come closer and closer to the real structure. So these are the natural frequencies and mode shapes. The damping ratio is a separate property of the structure, which gives a sense of how the structure would dissipate energy under dynamic load. We often look for this one in the case of seismic loading. So vibration testing, of course, comes in two main forms. One is so-called forced vibration testing, where we actually apply an excitation to the structure. And generally for dams, and this means very heavy equipment that have to be put on the dam wall, and you have to have lots of power supply to actually get the dam going. And the main idea here is that you measure the force that you induce on the structure, and you are able to derive or obtain the so-called frequency response functions directly. If one can do it, it is good to give you a very good result. However, it's very expensive, and preparation alone takes a long time. The tests don't take a long time, but the preparation and getting the equipment on site is not easy. There is the other type of testing, which is ambient vibration testing. And in this case, we are relying mainly on operational excitation, on operational loads. It could be just water waves, wind, or if you have got some generators and whatever gives the structure some excitation, we can use that excitation to obtain the response of the structure. So the main difference is that the forces that, or the excitation that is induced, we don't measure it, so we don't know how much, but we only look at how the system is responding to that excitation. So in the olden days, in the early days, it was viewed as very difficult and rather impossible, particularly for large structures such as dams. But over the years, this has fully matured. We have developed quite a few algorithms to analyze the data and extract the natural frequencies and mode shapes, but also the level of instrumentation and type of instrumentation has evolved to the extent now that we can actually measure ambient vibrations a lot more easier than used to be possible. And for this reason, it's therefore quite a very cost-effective method. One drawback, of course, is that ambient vibration testing itself, it takes longer than the force vibration testing farm on site. So whereas shaking the structure will take less than a minute, ambient vibration testing will take at least an hour of data collection. So you generate a lot of data before you actually can synthesize it into meaningful information. So ambient vibration testing is therefore, because I'm only talking about a device that I place on the structure, that's an accelerometer. I'll talk to these a little bit later. And a data acquisition system, in this case, it could just be a PC, you leave it on site, you collect your information. Because of this reason, we can use ambient vibration vibration for monitoring, which is for long-term monitoring of the structure. And because these dynamic properties are inherent, any change in the behavior of the dam will also result in change of the dynamic properties over time. So we can actually use this as the same way we use displacements for damage detection, for anomaly behavior, and so on and so forth. So it's got this dual action of providing us information for calibration, as well as for long-term behavior of our structural systems. So some observations from some monitoring of a dam here in the Western Cape over a period of time, monitoring the natural frequencies, comparing that to, particularly I'm interested here, I've just zoomed in to the water level. So this is the first natural mode, which is showing in red, and the blue is the water level. If you recall, the first observation I made was around the behavior, displacement behavior of the dam, that is very much in sync with the thermal behavior or seasonal temperature changes in the dam. This one is showing us that the dynamic behavior is very much in sync with the water level. So you can see there's a very good correlation between natural frequency and the water level. And this, we can also see that there is not much correlation between ambient temperature and the natural frequency, which means the ambient temperature is not affecting our natural frequencies that much. Doesn't mean there's no effect altogether, but the driver is mainly the water level. So we certainly have this possibility that has brought in these two, not competing, these two parameters together, which is the stiffness parameter and the thermal behavior. And thermal behavior in our case, in terms of displacements, is driven by the coefficient of thermal expansion of the concrete. This kinds of gives us another window in that we can use to access the behavior of the true behavior of the dam, which means we can determine the Young's modulus or relate the Young's modulus to the dynamic behavior, because we know that the frequency is very closely related to the Young's modulus and the mass. And we can look at the seasonal displacements, and we know they are very closely related to the thermal coefficient of expansion. So we therefore are not just updating the Young's modulus of the wall and the foundation, but we're also updating the thermal coefficient of expansion. So once we've got that idea, because this is the key here, once we've got that idea, it means that we can generate or develop an approach that gives us a neater solution that ensures that we don't either underestimate our foundation stiffness or underestimate our concrete stiffness, because we have tweaked the Young's modulus using the displacements to the point that it doesn't actually match the real behavior of the structure. So how do we take advantage of this? This is where ambient vibration testing becomes a source of good information. How do we take advantage of this to calibrate and validate finite element models? How do we say I have taken a measurement using ambient vibration testing, and I'm taking that measurement, combining it with temperature measurements to actually update and validate the structure. So how do we do that? We have come up with, over years, with an approach that takes a few steps. And I'm just going to walk you through that approach now. So this approach is a four-step approach, with the first step is what I would call dynamic calibration, followed by thermal calibration, and then displacement calibration, and then model validation. So in the observations that I made, there were two key observations. One was the relationship between the natural frequencies and the water level, which links to ambient vibration, and seasonal displacements with temperature. And so our first step really would be to deal with the calibration of the stiffness, then calibration of temperature behavior, and then calibration of displacements. Then we can validate this using any other data to say, okay, now once we've got a model, can I apply any other loading scenario and see if I get the same result? So how do we go about this? So in the first step in ambient vibration calibration is to obviously obtain ambient vibration measurements. We shall see a typical example here on Katzedem, how we did that for Katzedem. Once we've got that, we can bring it to our finite element model. And we have to then fine-tune the model to get the stiffness of the foundation and the stiffness of the wall. What one advises is, if, as much as possible, if you can determine the elastic modulus of the dam wall, so you can minimize the uncertainties on the stiffnesses, it means that you would only have to deal with uncertainty in the foundation modulus. And at the end of this process, you have your elastic modulus for the foundation, the elastic modulus for the concrete. And you don't want to change it afterwards. It becomes now your updated model. The next step would be calibration of thermal behavior. And here we generally apply the normal standard heat conduction model. I will just highlight some things to observe in the end of this with relation to, or rather in relation to temperature modeling. That this step of thermal calibration is really temperature behavior, so that I understand how the temperature changes seasonally inside the dam wall. Not many of our dams have got thermocouples installed in them to tell you what the temperature is inside and so on. But if one can get as much information as possible about the properties of that dam and thermal conductivity, that would be excellent, because it gives you the seasonal variation of the temperature within the dam. And this is not the displacements, it is temperature behavior. So we have to get this temperature behavior correct before we can estimate the seasonal temperatures. Once we convert those to seasonal temperatures, to seasonal displacements, we can compare these to the pendulum readings or geodetic readings to calibrate the coefficient of thermal expansion. So for dams that have got AESR, one has to also incorporate the long-term induced deformations from AESR. I'll show you how that can be done. And so the end of this process would be to say, I have the correct expansion behavior from the temperature, and I've also got the correct deformation behavior from AESR if there is AAR. Upon completion of these last three steps, one can then use either historical information. If I took a measurement 2 years ago, I can compare, I can take that scenario and apply the model to that scenario. There must be agreement. And it's always very tricky if you're doing this, but believe me, it works. Once you get to that process, you'll see the numbers just come together. Generally, they come together well. And at the end of this, you have a validated FE model, and you're ready to do your assessment, which means now you can do your prognosis. You can apply any loading conditions, and so on. A few things to note here is the modeling of the foundation really requires a good understanding of the site, and it's not going to be uniform foundation throughout. You'll probably have more than 2 or 3 areas of different stiffnesses. So the stiffness is not just a single number. It would be a series of values indicating the stiffness variation in the foundation. And the mode shapes really help us here to get to that stiffness distribution. Few things to consider and to think about. In the thermal analysis, I said that we apply the standard heat conduction models, but to get reasonable results, one has to account for solar radiation and irradiation, and this you can only do by understanding the position of the sun. We try as much as possible to incorporate that position of the sun on the dam during the day and during the month, and seasonal variation of the position of the sun. It sounds complicated, but it's not. We also, one has to obviously do a steady state analysis before you conduct your transient analysis. So temperature analysis would require that one goes through this process. It's not just applying a temperature on the upstream and a temperature on the downstream. It has to follow the seasonal variation of the temperatures across that dam wall. And of course, one of the challenges is the reservoir temperature, what the temperature of the water is. And I think it's one area that we still need to do quite a few studies on to understand the true profile of water temperatures in the dam. The other factor to consider is, of course, we talked about the mass of the wall and the added mass, which is the reservoir or the water. And in the modeling process, what we found is that the Westergaard method tends to overestimate the added mass by a significant amount, sometimes 20 to 25%. And we find that the fluid structure interaction approach, where you model the reservoir, is using fluid elements, depending on which software you're using. We find that this is a lot more, converges quite quicker compared to the Westergaard method, and generally gives results that are close to what we've measured. If you are going to deal with ASR, this is the approach that we have taken. It's not the only approach, but depending on the information available on the chemomechanical behavior of your concrete, this gives a much more realistic results. But like any other of these long-term projections, you may find that over a long period of time, which is what ASR does, the displacements may not be as accurate. So one would need to obviously constantly update these. So if you project for 10 years, you'll be fine. But after 10 years, you need to go back and measure and see, am I still on the curve? Otherwise, there are inaccuracies that are inherent in this method, like any other of these ASR-related approaches. So this is it's a very brief introduction to this subject, and I thought that I must, let me share something here. I thought that I must just walk you through very briefly, because the success of ambient vibration testing itself is largely dependent on what you use and what instrumentation you use. And there is a huge range of these instruments. So for our space, we have the vibration sensors. Those are the things that take the information from the dam wall and respond to the measurement. If I'm going to shake it, we've got to apply an excitation. We use what we call a shaker or hammer. And at this stage, we have relied a lot on wired systems because we are measuring very low level vibration. So we prefer to use wired systems. Hopefully, the wireless systems are getting better. I haven't used them at this stage. For the work that we do, we really want to get the best results. And of course, the data acquisition system is such a crucial element of this. So the choice of your vibration sensor, the cabling that you use, and the data acquisition system is the most crucial element, because that gives you the level of vibration you can measure, the amount of noise that gets introduced into your system, the length of cable that you can use. The system that we have chosen to use can obviously, at this stage, we are saying that we can measure down to a micro G, but one can practically say maybe 5 micro G. And the cables that we use can go up to 200, 300, 400, 500 meters on a single cable, because we shall explain them. We use this Honeywell accelerometer, and that is the so-called force balance, which means they're current driven, which means that you can have a very long cable without introducing noise. Voltage driven, you always have quite a bit of noise. So there is a bewildering choice, as I say, of these accelerometers and devices. So one has to be very careful if you are going to embark on this, which one you choose, because they may not actually pick the level of vibration that you want, especially under ambient. If it's forced vibration, maybe it will be good, but under ambient vibration tends to be, you want to have something that has a good resolution and something that is current driven, I would say. So of course, once you get to these current driven accelerometers, you're really talking quite a lot of money. They tend to be quite expensive, but in the long run, I think if you're working in this space, you get a good back for your money. Okay. And I spoke about the noise flow. For our accelerometers, we go down to about 1 micro G of accelerometer. Okay. This is what we teach sometimes when you teach about the actual how the accelerometers work. And I think this, I'll skip this one. The excitation systems. So if you're going to do forced vibration testing, there is quite a number of approaches. One is the instrumented hammer that you use to introduce excitation to your structure, and it will give you about 4 kilonewtons of force and get your structure moving. But you can move a dam with this one. We use this for floors and for bridges and building structures. They work fine. And this is the type, and this is how you introduce it. Not the way, not the guy below there. That's the wrong way of doing it. The one above is the correct way. You just drop it, you don't work the structure. This is a shaker. These are used for in not this size, but the sort of typical structure system to excite large structures. So you mount this on the structure and you connect it to a power supply, and it starts moving back and forth, and it will introduce excitation to your structure. So the most easy ones to use now is this electrodynamic shakers. We have got 2 of them. We use this to shake floors, to shake buildings and small bridges. This is how you introduce the excitation to the structure. And what comes out is of course these measurements. And what we do on site, as you will see in the next presentation, is that we spend of the 2 hours of measurement, we would spend maybe another hour plus ensuring that what we're measuring makes sense. And that's really the big deal. It's a big deal to understand that what is coming out of my device makes sense. The next most important element of ambient vibration testing is the acquisition system. What do you use to collect the information? So I've got my accelerometer, and I've got of course, maybe I don't need, for ambient vibration testing, I don't need the excitation stuff. But now I need to buy the thing that will read the accelerometer. And that's the data acquisition system. And again, here there is a wide range of them. But the important things are around how many measurements do I want to take at a given time? What's the size of this thing? Can I power it on site, or does it need extra power? And more importantly, how many bits? Okay, how many bits can I measure? The higher this number, the better. So the standard now is 24 bits. If you're less than 24 bits, it's not going to work for your ambient vibration testing. It's going to be a challenge. So there's also quite a range of them, and the range of suppliers. One has to make sure that the sensitivity and the lowest voltage I can detect on this matches the lowest vibration that I need to measure. So you get a range of these. One has to be very careful how we choose them. The dynamic range is generally also, once you've gotten the correct bits, if you get the correct bits, then it's not your problem. This is how a bit does, what a bit does. And so you see it's not a smooth measurement. It's a rugged, it's got these steps. If I've got the correct bit, then you get a smooth measurement. So with ambient vibration testing, again, one has to be careful what we choose for this. Aliasing, this is more electrical stuff, and one can put this together. So our setup would look something like this on site with a PC, a data acquisition system, and the accelerometers and the cables, and we distribute these to take our measurements. And so data quality, like I said, is absolutely crucial because the data comes raw in this way, and one has to be sure that what they're showing is, or what they are measuring, makes sense before you leave the site and before you actually commit to taking the measurements. So I would like to end it here now at this time on the basics of ambient vibration testing. I have introduced the idea how we combine other techniques, monitoring with ambient vibration testing for model updating, and the sort of instrumentation that one needs to achieve a good ambient vibration setup. Now I'll hand over to Dr. Nyoni to just walk us through a typical test and the results of that test. Dr. Nyoni.
Good afternoon, everyone. Just sharing my screen. So I will be walking you through typical ambient vibration testing, typical ambient vibration testing of a dam. So in this case, it was Katse Dam. So what I'll be presenting on, I'll do a brief introduction of the dam, and the relevant information to ambient vibration testing. Then now look at ambient vibration testing, the steps we followed in the test, in conducting the test, and look at a few results and some conclusions. So the Katse Dam is a dam which is owned by the LHDA, the Lesotho Highlands Development Authority. It was constructed in 1997 and it has a height of 175 and a crest length of 710 meters. Some key features of the dam are shear keys, preformed joint, and seismic belt. We conducted ambient vibration tests, and the objective of the tests So the objectives of the test were to determine the dynamic properties of the dam in light of monitoring of the long-term monitoring of the dam, and to assess if the seismic belt affects the dynamic behavior of the dam through the ambient vibration test, and to assess the response of the structure at foundation level. So the ambient vibration testing steps we followed were as follows. One was before we could carry out the test, we needed to get a sense of the model shapes and the first natural frequency to expect based on the water level of the dam. The second, thereafter, we then conducted preliminary ambient vibration measurements, so through an initial site visit to be able to assess if it be feasible to carry out the tests. And once we determined that it was feasible to carry out a full-scale test, we carried out a full-scale ambient vibration test. In the theoretical assessment of the dam, we used for the natural frequency, we used two approaches, which are shown there as equation 1 and equation 2. From the first approach, the first natural frequency for the water level for a full dam case was 2.13 hertz, and the second approach gave us a first natural frequency of 2.05 hertz. If you have a model, then you can run a dynamic analysis to be able to obtain or observe the sequence, the mode shape sequence, where from looking at which mode shape comes first. In this case, as you see, for Katse, it was an antisymmetric, which would be this type of mode shape as the first, and this would be the first symmetric mode shape. And then as the mode shapes numbers increase, then you get the also still you do get symmetric, but the number of troughs and increase as the mode number increases. So in this case, this natural frequency sequence, which was conducted for similar dams. For a similar dam, although it was not as high as Katse, and based on the classification, we would see that for a thick ash dam, typically you start off with a symmetrical mode shape, and for thin arch to medium arch, you'd generally have an anti-symmetric, and also depending on the type of valley or valley shape you have, whether it's a U-shaped or V-shaped or a wide or narrow valley. So for our initial, once the next step from getting the adjusted theoretical and initial estimate of the natural frequency and the mode shape sequence, we undertook an initial site visit to verify access, safety, and to conduct preliminary measurements. So access on site, conditions and safety requirements were carried out, and we also then conducted, while it was still on site, we conducted a preliminary measurement in Gallery A. I'll show it in a few slides. And we set up on blocks 5, 17, and 19. So the equipment we used was 3 force balance accelerometers with nominal sensitivity of 8.8 V per G, and a portable 24-bit natural instruments dynamic signal analyzer, and our laptop we had carried along. So what I show here on the left, let me just change it to a pointer, is an auto power spectra from the measurements. And we see the first 2 and 3 more shapes, because we didn't run the test for a long period. So we only picked the first 3 modes. But what this test showed was that we were able to carry out the what we confirmed to us is that we're able to carry out the tests based on the conditions of the site. And we were able to confirm that we have direct access to the galleries, and as you can see, the first 3 natural frequencies there was 1.8, 2.37, and 3.0. So this gave us a sense of what we can expect. So typically, because of the range of the first natural frequency being 1.8, the first 10 natural frequencies we're anticipating would be below 20 hertz. So then this became a guide for the full ambient vibration test, which we conducted. So for the full ambient vibration test, we used 22 force balanced accelerometers with the same sensitivity. And then in this case, we had a 24-channel purpose-made power supply and a 24-channel data physics signal analyzer, a desktop, and some cables. So the cabling had to be long in this case also because the dam is a very long crest. So our cabling got to about a kilometer in this case to be able to for the setup on the top gallery. So we set up on 3 galleries, which was the top gallery, which is Gallery A, and we did another setup on Gallery D, which was a bit in the middle of the dam, and we also set up at the foundation level, which was Gallery M, indicated in the images. So what we then observed, the typical result was for gallery A, the frequency response function. We can see that we have about 9 peaks, 1, 2, 3, about 9 peaks, which we identified for gallery A, which we also, now when you compare the result for gallery A and D as well, you see that the results match. So which means that the same frequencies we identified in gallery A, we also identified in gallery D. In gallery M, there was no downstream radial mode shapes which were identified. But what you see from gallery M was vertical movement, which at the stage where the explanation of where this is coming from was not clear. They had at Katse, they do have generators which generate a frequency, a natural frequency around 1.7, but the frequencies we have here are out of that range. But the generators we could pick on the gallery A vertical measurements or responses. And so the gallery A mode shapes, we identified 9 mode shapes, with the first being 1.81 and being an anti-symmetric mode, and the second mode being 1.95, which is a symmetric mode, and so on. And then if you look at the mode D motor parameters we obtained, we also obtained a similar modal sequence or mode shape sequence as that obtained in gallery A, with the first natural frequency being 1.8 and an anti-symmetric mode. So the usefulness of this data then is, as it has been indicated, is the natural frequencies are used in the updating process. Here I just show a typical, just including the displacements or displacements of the dam, but you typically use these results in updating an FEM model. And just to give a sense of the sensitivity, this was a sensitivity not for Katse dam, but for a different dam here in South Africa. But this gives a sense of the typical sensitivity one expects for an arch dam. So you see that the natural frequencies have a higher response as compared to the displacements in this case, and the change for, so if your foundation is stiff, if the foundation stiffness is less than that of the wall, then you are typically expecting a rapid change in your natural frequencies, which is but as the stiffness of your wall, of your foundation increases, then the change in natural frequencies due to the system stiffness, so the values above 1, then reduces. So the most sensitive part is below 1. and obviously because it's a dynamic response, the density of your wall also is more sensitive to any change in your density of the wall results in a change in the natural frequencies, but no change was observed there for your displacements, and the Poisson's ratio, also this sensitivity was not as much. However, if you look at the coefficient of thermal expansion, the sensitivity of the dynamic response is very small, but the displacements response is quite high compared to the dynamic response. So based on this, the ambient vibration tests therefore are used in updating your system stiffness. So just some concluding remarks. It's that 9 mode shapes were identified for KZM, and the identified mode shapes show good agreement with the expected theoretical modes of a medium thick arch dam with a U-shaped valley. The second conclusion is that there is no identifiable influence of the seismic belt, which was part of the objectives of this test, on the radial mode shapes of the dam. So based on the modes of gallery A and D exhibit the same mode shapes. And then we also conclude that the vertical modes of vibration identified in gallery A are consistent with the modes identified in gallery M. The measured response of the dam at foundation level did not indicate any dam structural movement. This indicates that the stiffness of the foundation material is approximately equal or greater than the stiffness of the dam. And lastly, based on the mode shapes, the right flank appears to be stiffer than the left, which would be important when you are updating or calibrating a model using the motor parameters from ambient vibration testing. So those motor parameters, it's not only the natural frequency one looks at, but also the mode shape, and the difference in stiffnesses, which is typically identified in the mode shape. So in this case, the right flank appeared to be stiffer than the left flank, and in the mode shape, once we pick out the actual values, those values can be used to compared to the values obtained from the model, and the model updated accordingly. So I think this is the testing and the use of and the explanation a bit on how the results from the test were then used for the model updating case. I think my presentation ends here for now.
Thank you so much, Dr. Nyoni, for the presentation, and Prof. Moyo, appreciate your time and for your efforts in preparing some information for us. I would like to open the floor to some questions. You can just raise your hand and I will activate your mic to ask your question directly. Otherwise, you're welcome to type it into the chat. Yes, we have Comfort. I have activated your mic. You can unmute yourself and ask your question.
Thanks, Ashley. Afternoon. I don't know if I'm audible.
You are audible. Thank you.
Okay. Afternoon, Prof. and Dr. Nyoni. Thank you so much for a good presentation. My question is a quick one. Looking at the 4 steps that you've highlighted in terms of approach to AVM, there are instances where you would not have, say, even your displacement measurements to do your calibrations. So in instances where AVM is the only tool that you have to do, say, your model calibration, what degree of confidence can you assign to that model in terms of giving you the sort of indication of how the structure or the dam is behaving? Thank you.
Yeah, thanks, Comfort. It would be the same. One could give a reverse question to say, what degree of accuracy do you get if you had not used AVM? So it works both ways. I think the uncertainties become high if you don't have enough measurements. And of course, the whole essence of assessment is to gather as much information as possible. The more information, the better. And with less information, you can invoke your engineering judgment really to say, okay, this makes sense or it doesn't make sense, depending on where the structure is and what your other information is telling you. So in an ideal space, it would be good if you don't have the measurements at all, to take course to look at the material properties of this of the system, and to do your coefficient of thermal expansion measurements. This can be done in the lab as well, and so you can minimize the level of error that way by collecting as much information on the structure as is, and that one says the best you can do. But to do the assessment without any measurement at all is again on the other extreme, I would say. So one would encourage that you do something to collect as much information as possible. Thanks.
Thank you. We have 2 questions in the chat. One is directed to Dr. Nyoni. He's saying that you far exceed his expertise. With regards to Katse Dam, are you aware of the structural anomaly in the right bank geology, referring to your point number 5 on the current conclusion side?
Sorry, yes, I am aware of that, and I think that is the ambient vibration testing also indicates that there is something happening on that length. So I think it helps you when you identify special if your foundation is not uniform, which was the case for KZM so-called, which confirmed a result which was already known.
Just to add there that ARQ actually, Ryan did a lot of work on this and on the updating using some of these measurements. And yeah, and I think if he was around, he had made some observations as well. Thanks.
Right, we have another question saying, thank you for your insightful presentation. You mentioned the importance of continuous monitoring of dams. In other infrastructure such as bridges and buildings, even small cracks can lead to measurable changes in natural frequencies. which are useful for structural health monitoring. However, given the massive and thick cross-sections typical of dams, I'm curious to know, would similar crack-induced frequency changes still be detectable in dams, or are there limitations in that regard?
Certainly, depending, of course, on the size of the crack, remembering also that essentially the natural frequency changes according to the stiffness and the thickness. So it depends on the depth of the crack. So it's your old classical EI over 12, ET cubed over 12, that second moment of area. That's what really EI is, what constitutes your stiffness. So the crack will, but not minor cracks. The significant cracks may cause changes. Yes.
Thank you. Ryan, I have allowed your mic. You can unmute yourself and ask your question.
Hey Ashley, how are you?
Hi, thanks.
Good, good. Hi Prof. Moyo and everyone, and Bukosi, Dr. Nyoni. Yes, I just wanted to add to what Prof. Moyo said. At Katse Dam, there are various geological features in the foundation rock mass. And obviously when we worked with Prof. Moyo and his team, where Prof. Moyo actually did the ambient vibration testing, and he gave us all the data, and we derived a finite element model of the dam and foundation, which we calibrated according to his ambient vibration testing. So the testing data that he gave us was very good quality, and we were able to calibrate our model very accurately. And yes, indeed, the features in the geology obviously made an impact. There's various forms of jointing and flow contacts in the basalt. So it's basically a basaltic rock with various zones of breccia and amygdaloidal zones, vertical, horizontal jointing. So all of those things were incorporated in the model as a first iteration using E-moduli from the design report, and then obviously fine-tuning those E-moduli according to the mode shapes and frequencies which our model gave us from the eigenvalue. So yes, definitely the geology impacts that, and the ambient vibration monitoring actually detects that as well. Thank you.
Thanks, Ryan, for that input. We appreciate it. We have another question. Says, first of all, thank you for the presentation. Congratulations on the work you have done. In your expertise and the different cases of dams you have studied, and focusing on structural damage, how should we approach damage, cracking, reduction in stiffness, etc., using environmental vibration monitoring? What would be the minimum variation you would consider to indicate damage?
Yep, that's a big one. And you will notice that we can measure to the nearest point 0.01 of a hit. And therefore, anything that varies away from that level becomes suspicious. So a lot of how much you can detect on the variation in the natural frequency depends on the resolution of your instrumentation, which is why I emphasized the idea of having the correct instrumentation. Practically 0.02, 0.03 will be a significant change of a hit. Also, as you could see, that a change of almost, you can also measure it from the point of view of almost a meter change in the water level changes the natural frequency quite significantly. So you can almost gauge from from that point of view. And it, like any other devices or like any other process, there is always uncertainty, particularly with our systems, dams, and civil infrastructure in particular. The level of uncertainty is high, so we can't give a number. We can give a range in many cases. But where there's a deviation, the deviation becomes obvious. So I would say that yes, ambient vibration in combination with all the other types of monitoring systems is a very good approach to gather as much information on the behavior. And one has to understand what the benefit of that is to the system. And with this for dams, we understand that to discriminate between thermal and static loading or deformations from the stiffness, you have to do this type of measurements. Otherwise, you can't easily discriminate between the two. Thanks.
Thank you. Alban, I have activated your mic. You can unmute yourself and ask your question. Alban, we're not hearing you. Okay, I'm going to move to another question.
Can you hear me? Hello?
Yes, we can hear you.
Sorry, I just activated the microphone. Thank you very much, Professor, for the presentation. It was very interesting and very opening to discussions for the future. My point is a bit connected to the previous colleagues. For instance, we have a lot of indicators for damage in several types of structures, including dams. However, in the context of a long-term monitoring system, basically we have just two parameters over time. We have natural frequencies and mode shapes. On the other hand, we can have a crack deterioration over time, a landslide or a geotechnical differential settlement, or a hazard like earthquakes. In the case of earthquakes, it is easy to detect anomalies in the structural behavior in terms of frequency reduction, abrupt frequency reduction, or also a bit more statistical parameters, for example, t-square statistical parameters and so on, in terms of control chart. In any case, the reality of dams is we have a slow deterioration over time. How can you quantify it over time, this small deterioration of structural stiffness?
Yeah. So in essence, as you see with the sensitivity analysis that Dr. Nyoni presented, one can more or less actually is writing a paper now on something along those lines. You can work out how many how much change in the Young's modulus and how much change in the frequency yes, how much you accumulate. And it's obviously for civil infrastructure, it's not always easy. And however, where there is a deviation, you will pick that up. And I think one can go back to my earlier comment that if you start to look at about 0.01 hertz to 0.02 hertz change, and this is very clear from our monitoring, long-term monitoring, that if you start to see that, if I measure 2.01 now and I measure 2.03 later, those will be totally different. The structure would have changed. In our case, that is coming out of the water level rising or changing. So it is sensitive to quite significantly sensitive to those changes. And one of the aspects that we have to be careful about with these is that it has to work with other methodologies as well. So it's not saying AVM on its own. And I want to emphasize that it's a collection. It does bring a dimension that helps us to eliminate certain things. You know, at the end of the day, we have not really experienced a dam that has shifted in behavior that we could have as a reference to say, oh, we saw this one there. However, it is clear from our measurements that if there is something happening, you will pick it up.
We have also alkali aggregate, sorry to interrupt, alkali aggregate swelling of concrete, which is over time phenomenon, and that affects the Young modulus, or a partial portion of the dam affected by the alkali aggregate. So
yes,
in that case, it would complicate a bit more because it's not a global reduction, but a local reduction of the stiffness. Yeah.
Yes. So again, that's a very tricky subject. In which what we have done is to investigate the so-called internal stiffness or geometric stiffness. So it's an inherent stiffness that it builds up in the dam because of the expansion. So Dr. John has done quite a bit of work in that area. And interestingly, it's not that sensitive. The one thing that becomes sensitive to it is the actual, now it's the deformation, the actual displacement, a lot more sensitive because the overall stiffness change due to ASI is not huge.
Okay.
Yeah, that's our observation, at least at this stage.
And the last thing, sorry, I put a lot of questions. I could talk weeks about this. Did you find difficulty in removing environmental effects? For example, the dams are very affected by temperatures, especially arch dams, aside from the variation of water level. Did you find difficulty on removing this in order to cleanse the data, in order then to post-process the frequencies?
Yes, and this is the essence of the whole system. It is that we have to do a real thorough thermal calibration so that we can separate the two. And that's really the whole bottom line of this is depending on where you are located, thermal can be the main driver. In our case here, where we've got large seasonal temperature changes, so we have to be able to separate so that we don't miss
the seasonal and the daily variations.
Yeah, mainly the seasonal for large dams. So yeah, so that is really the crux of the problem here, is that they will have an effect, and sometimes you don't, over time, you may mistake the thermal effect for something else, unless you can remove it or understand it and how it actually affects the behavior of the structure.
Okay. Thank you very much. Thank you.
Thank you.
Thank you for that discussion. We have two last questions in the question and answer section. Saying we once had some issue with very low ambient vibration resulting in useless data, despite being on a large dam. We wondered if weather conditions or water level had an impact on the acquisition, water level was low, is it better to have a full lake or empty lake to proceed with those testings?
Yeah, so it is it's better to have some significant ambient activity, if I may call it. The full dam generally does that for you. So when we test the dams full, we generally find it's easier to get the response. However, depending on where you are, it is possible to spend hours and not get the appropriate response. And the type of instrument that you are using as well plays a role. Our rule of thumb is the weather. So we tend to look at the weather. When the weather is not at its best, that's when we do our testing. So we appreciate when the weather is windy and depending on where you are, if you go during the day and everything is calm, it's very likely that you're gonna have to spend a long time measuring because to build that data is difficult. So generally, typically, you watch out for the times when there's a little bit of wind. That's to generate the waves on the lake, as well as if the dam is empty on the wall itself. That would be my advice.
Thank you. Our last question then is for Dr. Nyoni, saying with reference to point 4 on the conclusion slide, could you please specify where sensors were placed in the dam at foundation level? And generally, would you expect a different response, in other words, structural modes at foundation level, even with differences between foundation and dam stiffnesses?
Okay, so the sensors were placed, let me just get the slide. They were placed generally shown by the green triangle there, okay. And the other question was, sorry, can you just clarify the other question for me? So we placed them on as shown there in the image, so which means that we set up about, I think it was 6 or 7 points distributed along the base of the foundation. Then there's question on, please repeat the question on the difference.
So he's asking, would you expect a different response, in other words, structural modes at foundation level, even with differences between foundation and dam stiffness? Giovanni, if I'm not reading the question correctly, you can just raise your hand and then we can open for discussion.
I think I understand the question. So I would expect a difference in the behavior, particularly the mode shape. So I've seen in the studies that I've done that the stiffness, so if the system stiffness varies, it also affects the mode shapes. So as an example, if your stiffness, so if you compare, let's say if you fix, so I'm now talking from the motor side, if you fix your boundary condition between the foundation and the wall, sometimes depending on how low your values are, you might get a change in the sequence of the natural frequency. So the stiffness does affect the motor parameters, not just in terms of the natural frequency, but also in terms of the mode shapes.
Giovanni, your mic is loud. You can unmute yourself and ask an additional question if you want. We are not hearing you. Okay, I'm going to assume that his question is covered. He can't unmute himself at this stage. So I'm just going to assume that the question is covered. And then I will just move on to the last part. Right. Once again,